Welcome back to machine learning. This video will cover support vector machines and kernel methods. We'll start with SVM and we'll actually break it up, covering kernels in the middle, and then we'll end with SVM. Let's start with a motivating example. What boundary would you say is best? Let's say each boundary corresponds to a different model. Which model would you say is best? Probably the green one, right? Why? Because it gives the most space between the two classes. This distance is referred to as the margin. We want a model that gives us a large margin. That is, the hyperplane is far from both classes. And if we maximize the margin, we'll get the best hyperplane. Support vector machines, or SVMs, give us the hyperplane with the largest margin. How do we find the hyperplane with the largest margin? By solving a constrained optimization problem. Let's just hold on here for a second. What just happened? Let's break it down a little bit. An optimization problem just means that we want to find the values for W and B that minimize that first expression. And the problem is constrained because we have the additional constraint in the subject to line. Gamma is the margin. So we're trying to minimize 1 over gamma, which is the same as maximizing gamma. And the constraint just says that all training samples have to be correctly classified. Remember y times y hat being greater than 0 as the constraint for not updating the perceptron? This is the same idea. What happens when the data is not linearly separable? That means that we can't satisfy the constraint for every sample, and the so-called feasible region is empty. The feasible region contains all possible solutions to an optimization problem. If there's no solution where the constraints hold, then the feasible region is empty. In this example, we have green points and black points. They're all mixed together, so we wouldn't be able to draw a line and perfectly separate them. This formulation of an SVM is only good when we have linearly separable data. It's called a hard margin SVM because the constraints are hard. We want the SVM to be a little bit more flexible so that we can handle nonlinearity and nonlinearly separable data. We do this by introducing so-called slack variables. The slack variables penalize the optimization problem for each incorrectly classified sample. We can think of the slack variables as moving the sample across the boundary. It doesn't actually move the point. It applies a penalty equivalent to the distance it would take to move the point across the boundary. Each point is given a slack variable, even if they're correctly classified. If they're correctly classified, then the slack variable has a value of 0 because there's no penalty for that point. Let's look at this example. Again, we have green points and black points. There's a couple black points that are intermixed with the green points, and so we can't draw a line that perfectly separates the data. This line does a good job, getting only 2 samples incorrect. For all the samples that are right, the slack variables are going to be 0. But for the 2 that are incorrect, the slack variable is going to be greater than 0. This is called a soft margin SVM. Now we have additional constraints, and these crazy letter xi's are going to be our slack variables. What is C? C is greater than 0, and it controls overfitting. If C is low, then we don't care so much about mistakes. If C is high, then mistakes are very costly. What's nice about the soft margin SVM is that the feasible region is never empty. We can always find a solution to this optimization problem. This optimization problem is very similar to the hard margin SVM, where we have minimizing 1 over gamma, which is maximizing gamma, which is maximizing the margin, and then we have this additional term in the minimization. These are our slack variables, and they have to be greater than or equal to 0. For all of our correctly classified samples, they're 0, so that's already minimized. But for all our incorrectly classified samples, they're greater than 0. So we want to minimize the number of incorrect classifications. Our constraints are similar. This constraint is, again, we need to get all the samples right, but now we can get some wrong given our slack variables. And all the slack variables have to be greater than or equal to 0. Okay, we wrote down an optimization problem. How do we solve it? First off, how do we measure the margin? Let's assume that someone gave us a W and B and we want to calculate the margin. The hyperplane will be exactly halfway between the nearest positive point and the nearest negative point. If not, the margin could be made bigger by simply sliding it one way or the other by adjusting the bias B. Let's look at our equality constraint. From our optimization problem, we had yn w dot xn plus b is greater than or equal to 1. So let's figure out what points need to be equal to 1. Those are going to be our support vectors. So let's look at this constraint. Let's take a positive point and a negative point here to figure out how we measure the margin. Our positive point is going to be x plus, and our negative point is going to be x minus. W dot x plus b equals 1, and W dot x minus plus b equals negative 1. Remember, we have to multiply by this yn. For the negative point, yn is negative 1. This is where some of that linear algebra comes in. We're trying to measure the margin, so we need to figure out the distance between x plus and the hyperplane and x minus and the hyperplane. In order to find the distance between a point and a hyperplane, we need to project the point onto a vector that is perpendicular to the hyperplane. W is perpendicular to the hyperplane and points in the direction of the positive class. So we need to project x plus and x minus onto W, but the only way we can do that is make sure that W has length 1. So we divide W by the length of W to get a unit vector here and here. Then we can take the dot product of this with x plus and with x minus, and then add b. And that will give us the distance from x plus to the hyperplane. Here we have negatives. That's because we moved the negative from this side back over here. So the distance, the positive distance, that is the distance from the hyperplane to the positive point, is this, and the distance from the negative point to the hyperplane is this. We know that the margin is 1/2 of the distance between those 2 points. So we simply have this, 1/2 d plus d minus. Now we just plug in d plus and d minus, and we have this equation. Now we do a little bit of algebra. We take out 1 over the length of W from this whole expression here, and we have this. Now let's remember that we're working with our equality constraints. So we have W dot x plus b equals 1, and W dot x minus plus b equals negative 1. So now we have 1 minus negative 1, which is 1 plus 1. And simplifying this whole thing, we get 2 over 2w. And so we have 1 over the length of w as our gamma. What does this mean? This means that the margin is actually equivalent to 1 over the length of w. So we can change our optimization problem where we can replace this with the length of w. So now instead of trying to minimize 1 over the margin, we're just trying to minimize the length of w. Here, we're going to minimize the length squared, and we're going to add a little 1/2 here, and that just allows us to have nice derivatives, but it's not actually going to change the solution to the problem. A large margin gives us good generalization. That's why we like it. The first term in the optimization problem gives us a large margin, and the second term gives us a small slack. Large margin, small slack. That is minimizing errors. Let's say that someone gives us a W and B that solve this problem, and they forget to give us the slack variables. Can we recover them? Yes. Let's look at a positive example, xn, and let's find xin. So we have a sample that's labeled as a positive class, and we want to find what the slack variable is for that particular sample. There are two cases. Either we got it right, which is this, or we got it wrong. So either the sample is correctly classified or not. And if it is, then xin is 0. But if it's not, then let's calculate what yn times w dot xn plus b is. Yn times w dot xn plus b is 0.2 in this example. I'm just saying that. I've decided. Because you have the values, you have the sample, you have w and you have b, and you know the label is 1. So you can actually calculate this value. Then if we set xin to 0.8, that would make it such that our point now satisfies this minus xin. Now our point satisfies this equation. We can use the following formula to do this in general. So if we're given w and b and we have a point xn with its label yn, we can use this formula to calculate what the slack variables should be. All this says is that if I got the sample right, then the slack variable is 0. If I got the sample wrong, then the slack variable is 1 minus the prediction times the label. Then we can change our optimization problem, given this definition of xi. This is a hinge loss. We may remember this from a long time ago when we talked about loss functions. The hinge loss is just like this. It's the maximum of 0 and 1 minus y times y hat, which is exactly what the definition for the slack variable was. Don't worry too much about this definition because we'll mostly talk about it in terms of slack variables and not a hinge loss. This is how we'll talk about it most of the time. Why is it called a support vector machine? Because the points, that is, the vectors that determine the margin and the hyperplane are called support vectors. You can think of them as supporting the hyperplane, keeping it in place. Here we have this solid black hyperplane. The margin is defined by this distance here, which is equivalent to this distance here. The support vectors are these 3 circled points. If one of them were to move, the support would change and the hyperplane would move. So you can think about the support vectors as the minimum number of points required to hold the hyperplane in place. The idea here is that we want to optimize this equation by finding xi that work for a given w and b. Since there's a finite number of points, it means that we have a finite number of w and b we can check. We're going to take a break right now and talk about kernel methods for a little while. Kernels are what make SVM so powerful and useful. Kernels allow us to do feature expansion for free. What's feature expansion? Let's look at an example. The XOR problem has data like this. This is something that's not linearly separable. We've talked about this a couple of times in class. We can actually do feature expansion where instead of having 2 features, x1 and x2, we can add a third feature that is a combination of the other features. So if we create a new feature, x3, that's x1 times x2, our data will look like this. So instead of having 3 features, we'll actually just have 1 feature that's a combination of the other 2, and our data is suddenly linearly separable. We can do all kinds of different feature expansions using the features that we have. Kernel methods allow us to do feature expansion. I'm going to use this word for free a lot. We'll get to the point of that eventually, but the idea is feature expansions are kind of costly, especially if you expand to a much larger space. So for the XOR problem, we actually reduce the dimensionality by replacing two features with one. But most of the time, you're just going to add the extra features on the end, and so suddenly you can have huge feature vectors. Kernels allow us to take advantage of feature expansion without actually having to expand the feature vectors into the new space. We'll go into detail in this. A quadratic feature expansion may take a feature vector like this, where we have n features, and it may produce something like this, which is humongous. This gives us all quadratic operations on every single feature. So that's x1 to the 0, which is 1. Then we have x1 by itself, x2, x3, and so on. The 2's here are just to allow everything to be a little bit more simple, but it doesn't change anything. And then we have x1 squared, x1, x2, x1, x3, and so on, all the way up to xd squared. The d here and the n here don't match. That's because I stole this from somewhere else, and I was using n, and they're using d, but don't get confused by that. We could transform the features into this new space and then train a classifier in this space. There's two problems with this. The learning algorithm scales linearly with the number of features, and we may need many more samples to avoid overfitting. Think about the perceptron. The perceptron has a W and a B, and W is the same length as the features. So if we expand our features quadratically, we have to expand the size of W quadratically. So what we want to do is never explicitly calculate phi of x. That is, we never want to explicitly calculate the feature expansion. The only way we can do that is rewrite our algorithm such that w dot phi of x can be written as the dot product between samples. So we've learned about perceptrons, we've learned about neural networks, and SVMs are very similar in that we have w dot x somewhere in the algorithm. We want to replace w dot x with x dot z, where x and z are both samples from the training set. This phi is going to be our expansion. So assume we've expanded the features, and then we want to take the dot product. And once we have everything in that form, we're going to be able to remove this operation and replace it with kernel operation, so we never actually have to explicitly calculate phi. We have all these nice methods that give us linear decision boundaries, like the perceptron and the SVM. Many problems are nonlinear, so we want to be able to use feature expansion to solve these problems in a different space. The problem with feature expansion is that it requires that we know what the expansion should be, and if not, the expansions can be arbitrarily long. For perceptrons, we have a weight vector that's the same length as our feature vectors. So if we explicitly expand features, then we'll get a really long W as well. And then the dot products between W and expanded features are also really long. Instead, we want to stop working with W and instead work with samples only. Why would we want to work with samples only? Let's see why dot products between samples might be helpful. Assume we're using the quadratic feature expansion. If we expand the features first and then perform the dot product, we get some crazy long expanded dot product here. But if we do a little bit of algebra, we can actually bring it all the way back down into the original space. So we took an operation that was O of d squared and brought it down to O of d. This is the kernel trick. That is, we can perform dot products between expanded features in the original space. Let's integrate the kernel trick into the perceptron to allow the perceptron to solve non-linearly separable problems. Let's go through the perceptron algorithm and replace every instance of x with phi of x. Here, we did it. We replaced x in two places, when we were calculating the activation and when we're updating the weight vector. What's the real problem here? W. We don't want to use W explicitly because now W is going to be as big as our feature expansion. So how can we replace W? Well, let's figure out what W actually is first. In the perceptron algorithm, we initialize W with 0. So when we first start off, W is 0. And then we only update W when we make mistakes. Let's run through an example and see how W gets updated. Let's assume we make our first mistake on sample x0. So now we update W using the update equation, and we get W equals x0, y0. Let's say the next time we update is on sample xi. Again, we update with the same equation, and now our W is x0, y0 plus xi, yi. Our third update is on xj. Now W is x0, y0 plus xi, yi plus xj, yj. This is starting to form a pattern, and we see that W is a sum of xn, yn, where xn is wrongly predicted. That means that we can rewrite W in terms of xn, yn. In fact, we're going to rewrite W like this, where it's the sum of alpha n's phi of xn. So what is alpha n? Let's look at our example again. If our first update is on x1, then W becomes x1, y1. So we can have alpha 1 be y1, and then W is this. If it's y1 here, x1 here, then that's what we have for W. Second update is on xi, yi. Then alpha I will be yi. If our third update is on xj, then alpha j will be yj. Let's assume we do a fourth update and it's on the first sample again. So that means that W equals 2x1, y1 plus xi, yi plus xj, yj. So alpha 1 is now 2y1. So alpha acts like a counter that's counting up the number of times each sample was incorrectly classified. And all you do is multiply that count by the label for that sample. So for all the samples that you're always getting right, it's going to be 0. But for samples you get wrong, it's going to be the label for that sample multiplied by the number of times you got it wrong. And this is our new W. Look, we've replaced it with a sample. So if we put that in our equation, Wx plus b, then we end up actually with a little bit of algebra, we end up with dot products between samples. We did it. If we replace that W in the activation line, we now have this. We can similarly replace the W down here with this as well. Now we've created the kernelized perceptron, and we can basically perform feature expansions for free. What does that mean for free? Well, we're having to do quadratic feature expansion by expanding the sample, expanding W, and then performing dot products in this space. Now we've brought everything back down to dot products between samples, which can be replaced by kernel products. So we can replace this operation here with a kernel of xm, xi. And that means that we're performing operations in the original space, but we're getting all the advantages of performing the operations in the expanded space without any of the negatives. So we're getting feature expansion for free. Okay, great. Now we've talked about the quadratic kernel, but what is a kernel in general? A quadratic kernel can only do so much for us. A kernel is defined by the expansion phi. That's this little guy right here. And sometimes it's called the kernel product. We can write our learning algorithms in terms of kernel products, never having to explicitly compute phi of x or phi of z. Remember that x and z are both training samples. This means we can add this nonlinearity for free. A kernel is basically any function of two variables x and z that can be expressed as a dot product of some transformation phi between those samples. So if we take a function and we can express it in terms of the right side above, that is, dot products between expansions of samples, then that function is a kernel. Can we use any k in our algorithms? No. K is only a valid kernel if it corresponds to a dot product between its arguments. That is, there exists a phi such that k equals phi of x dot phi of z. Remember the quadratic kernel? Phi of x dot phi of z reduced down to 1 plus x dot z squared. Any degree d polynomial can be written similarly. What other properties do kernels have? Any positive linear combination of kernels is also a kernel. That is, if ki is a kernel and alpha I is greater than 0, then this is also a kernel. The product of two kernels is also a kernel. And the scalar multiple of a kernel is also a kernel. Is there another way to check if something is a kernel? Yes. A function k is a kernel if and only if it is positive semi-definite. What does that mean? It must satisfy Mercer's condition, which is for all functions f that are square integrable, which is this side, the following holds. It seems like this came out of nowhere, but trust me on this, they're equivalent definitions. We're not going to go deep into this, but this allows us to find better kernels, more interesting kernels. We can use Mercer's condition to show that the Gaussian kernel, also known as RBF kernel, radial basis function kernel, is also positive semi-definite. The gamma parameter in the RBF kernel controls the width of the Gaussian bumps. What is the value of the RBF kernel when x equals z? It tends towards 1. What about when x minus z? What about when this term right here goes up? The kernel goes down. You can think of this kernel as a similarity measure. What does it look like? A linear kernel gives us a boundary like this. A polynomial kernel gives us a boundary like this. And the Gaussian kernel, or RBF kernel, gives us these bumpy regions. So that gamma controls the width of these bumps. Let's do a quick problem to solidify the idea of kernels before we get back to SVMs. Consider two examples. X is x1, x2, and z is z1, z2. That means we have two dimensions for our features. We have a kernel, which is x dot z squared. Now, I want to know, what is phi? The hint is to try to expand the right side to see if you can see a dot product between a function of x and the same function of z. So let's expand. If we take the kernel x dot z squared and we expand it using these particular features here, we have x1 z1 plus x2 z2 squared. Now, if we actually perform the square, don't forget to FOIL, we get x1 squared z1 squared plus 2x1 z1 x2 z2 plus x2 squared z2 squared. Now, we want to create phi by looking at each of these elements. So first, let's look at the first term. The first term can be broken up into x only and z only, like so. So we could take the dot product between x1 squared and z1 squared, and we would get this term. Okay, let's look at the second term. Let's ignore the 2 for now. We could take the dot product between x1, x2, and z1, z2, and we would get this term. Notice how there's x's in one and z's in the other. We're not mixing them up. Now for the third term, we could take the dot product between x2 squared and z2 squared, and that would give us this. Let's go back to this 2. If we need to multiply two things together to get 2, w and y, for example, then w could be 2 and y could be 1. But we need the function of x and the function of z to be the same. So with the constraint that w equals y, that is w squared equals 2, then w equals root 2. So this becomes root 2 x1, x2, root 2 z1, z2. We can actually put these together, taking the x only terms and making a vector, and then taking the z only terms and making a vector. And if we take the dot product between those two, we will get this. And they're the exact same function of these different variables. So I could take any variable, w, and square its first element, take the square root of its first element times its second element, and then take the second element squared. And that's my phi. So phi of x is this, right? And we need to make sure when we're doing this that the x side and the z side match exactly, because you're applying the same function phi to x and to z. So if they don't match exactly, then that's not right. We took a nice long break for kernel methods. Why? Because the power of SVM comes mostly from the ability to use kernels to solve non-linearly separable problems. So now that you understand kernels, we're going to dive back into SVMs to see how we can use kernels in the formulation we had before. The SVM tries to balance a large margin, that is, a small w, with a small loss, that is, a small slack variable. Remember that gamma equals 1 over the length of w. So maximizing the margin minimizes the length of w. When we talked about it before, we were given some w and we wanted to find xi for every sample. So we could test out every possible w and b and then calculate xi and find the combination that minimizes the first expression. That's kind of silly, right? Brute force isn't usually the best way to do stuff like this. So instead, we're actually going to introduce Lagrange multipliers to solve this optimization problem. Let's not lose sight of the goal. We're trying to rewrite the SVM optimization problem so that it no longer relies on W and only depends on samples. That is, dot products between samples through kernel products. What is the method of Lagrange multipliers? It's an optimization method to find the max or min of a function subject to equality constraints. Let's use this example where we're minimizing f of xy subject to g of xy equals 0. To solve this using Lagrange multipliers, we introduce a new variable, alpha, called a Lagrange multiplier. Then we study the so-called Lagrangian, which is this new function, which is a function of x, y, and alpha. If f of x0, y0 is a minimum of f of xy for the original constrained problem, then there exists an alpha such that x0, y0 alpha is a stationary point for the Lagrangian. What's a stationary point? A point where the first partial derivative of L are 0. Who cares? What does the Lagrangian formulation give us? It actually allows us to solve the optimization problem without explicit constraints. We're trying to solve the following optimization problem. We have n training samples, so we have 2 times n constraints, one for each of the constraints listed in the subject to line. Thinking about Lagrange multipliers, we had equalities. Now we have inequalities. Let's rewrite all our constraints so that they are something greater than or equal to 0. Then we'll be able to add the corresponding Lagrange multipliers. The second constraint is already good, and the first one becomes this. Now we're ready to construct the Lagrangian using alpha n for the first constraint and beta n for the second constraint. Don't worry, it's going to get worse. So this is really big and horrible to look at, and I know that, but eventually it's going to become very nice, and we're going to understand why we did all of this. Our new optimization problem is now this horrible thing. We want to minimize the Lagrangian with respect to WB and xi, and maximize it with respect to alpha and beta. If we're able to find a solution that satisfies our constraints, then alpha and beta can't do anything to hurt the solution. If we're able to find a solution that satisfies our constraints, then alpha and beta cannot do anything to hurt the solution. Let's do an exercise to better understand what this means. What happens to beta n when xi n is greater than or equal to 0? Well, we're trying to maximize L with respect to beta, so maximizing L is the same as minimizing this term. So if we know that xi n is greater than or equal to 0, we want to make beta n as large as possible, we want to make beta n as small as possible in order to make L as large as possible. because we have this negative here. Okay, what happens to beta n when xin is less than 0? Remember that xin is not supposed to be less than 0. It's always supposed to be greater than or equal to 0. So if it's less than 0, we already have a problem, and that means one of our constraints was broken. So what happens to beta n when this happens? Well, again, we're trying to maximize this, and xin is negative now, and so that's positive. This term is now positive, so we want to make beta n as big as possible. That means that beta n will tend towards infinity, giving this term a very large positive value, maximizing this expression. So if our constraint isn't met, that xin is greater than or equal to 0, then beta n will head towards infinity. But if our constraint is met, then beta n will be as small as possible. What happens to alpha n when this expression is greater than or equal to 0? That means what happens to alpha n when our constraint is actually met? When our constraint is actually met, then we want this term here to be minimized in order to maximize L. If our constraint is not met, then alpha n will tend towards infinity because this will be negative. So then we'll have a positive value here because of this minus, and this will tend towards infinity. So basically all we're saying is if our original constraints are met, then alpha and beta will tend towards 0. But if they're not met, then they'll tend towards infinity. So as long as our original constraints are met, alpha and beta won't do anything to harm the solution. It's only ensuring that the constraints are met. Otherwise, they blow up to infinity. We can solve the following equation by taking gradients. This is the so-called dual form of the SVM. We can take the gradient of L with respect to W. What's the goal? Our goal is to remove our dependence on W. So we can actually take the gradient with respect to W, set it equal to 0, and solve for W in terms of the other variables. So we do that here, taking the gradient of L with respect to W, and we get this expression. We set it equal to 0, and that means W equals the sum over all n of alpha n, yn, xn. We can take this expression for W and plug it back into L, removing W entirely. Now it gets even messier. We can actually simplify this to this. It doesn't actually look simpler, but let's try one more, and we get this. This looks terrible. What's good about this? There's no W, and everything is written in terms of dot products between samples. We should also remove B and xi. Let's try to remove B with the same method of taking the derivative and setting it equal to 0. If we take the derivative of L with respect to B, we get this. There's no B in this equation, so we can't set it equal to 0, but it tells us that B times alpha n yn term goes to 0 at the optimum. Now let's do the same thing for L xi. We get this derivative, which also doesn't have an xi in it, but it does tell us that we can rewrite the second term in that really long equation for L, and then we get this. It ends up canceling with the most of our last term, and so this is what we end up with. Remember that alpha n and beta n are constrained to be greater than or equal to 0. So if we remove beta from the optimization, we have to ensure that alpha n is less than or equal to c. Otherwise, beta n could be less than 0, which is not allowed. So finally, we have this, and we can replace the dot product between xn and xm with k of n xn xm. Maximizing L of A, L of alpha, is the same as minimizing negative L of alpha. So we can minimize this, and we can solve this using gradient descent. Now, I know that was a lot. Don't worry if you didn't follow all the algebra. The idea is that we can take our optimization problem for our soft margin SVM and convert it to a dual form using a tool called Lagrange multipliers. This allows us to make a constrained optimization problem easier to solve. We remove the constraints and put them into the optimization, known as the Lagrangian. Then we're trying to minimize the Lagrangian. All we did to get to this was do a little bit of algebra and substitute terms. And then we were in a position where we were able to have dot products between samples, and we could replace those dot products between samples with kernels. That's it. And then we can solve this kernel version of the soft margin SVM using gradient descent. Let's go through some examples. Given the following training data where red circles indicate samples from the negative class and green circles indicate samples from the positive class, what W and B would be found by an SVM? Let's assume all points have integer coordinates. We can solve this in several ways. Let's first think about it as a system of equations. I can find my support vectors, which in this case will be 1, 0, 3, 1, and 3, negative 1. From the SVM formulation, we know that yn w dot xn plus b equals 1 when xn yn is a support vector. So that gives us the three following equations. We can take the first equation and simplify. We can take the first equation and plug it into the second equation. And then we can take the first two equations and plug them into the third equation. This gives us W1 equals 1. Solving for the other variables, we get W1 equals 1, W2 equals 0, and B equals negative 2. We've done it. There's another way to solve this. We can use information that we know about SVMs, specifically that the margin is equal to the inverse of the length of W. That is, gamma equals 1 over the length of W. The steps for this method are as follows. First, we're going to find the direction of W. We're going to name that dir W. We're going to find the value of the margin, and then we're going to use this equation, gamma equals 1 over the length of W, to find W given its direction. Then we're going to solve for B using one support vector. Let's do it. Remember that W is orthogonal or perpendicular to the decision boundary. We can see from the plot that the decision boundary should be a vertical line like this one. So W should point in the X direction. It's also supposed to point towards the positive class. So it could be like this. We can say the direction of W is 1, 0. We could actually say 2, 0 or any scalar multiple of that. That's because directions are directions no matter the magnitude. The scalar multiple of a vector points in the same direction as the original vector. Now that we have the direction of W, we need to find the value for gamma. From the plot, we can see that the support vectors are 1, 0, 3, 1, and 3, negative 1. We care about the distance between the negative and positive class. In this case, it will be 2. This is something that we're just eyeballing at this point. We'll go over it a little bit more further. But there's a distance of 2 between this negative point and these two positive points. In general, if you have 3 support vectors, you want to create a triangle between the 3 and then calculate the height of the triangle. In this case, we can see that the negative point bisects the positive 2 points. That is, it cuts it in half. So we can calculate the distance between the negative point and halfway between the 2 positive points. And the distance here is 2. Gamma is going to be half of that. So in our example, gamma is 1. So now we have the direction of W and gamma. We know that gamma equals 1 over the length of W. So that means that the length of W must be 1. Well, we need to take the direction of W and make it a unit vector, because then when it's a unit vector, it has length 1. And when it has length 1, we can multiply it by the length of W and we'll get W. So we calculate the length of the direction of W and it ends up being 1. So it's already a unit vector, so I don't have to divide it by its length. But I do need to multiply the direction of W with the length of W, which is 1. So we take the direction of W, we calculate the margin. We use the margin to figure out what the length of W should be, and then we normalize the direction of W and multiply it by the length of W, and that gives us W. We can do the exact same thing if we had assumed that the direction of W was 2, 0. If we assume that the direction of W is 2, 0, our margin doesn't change, so the length of W is still 1. Now, the length of the direction of W is 2. So we take the direction of W, divide it by the length of the direction of W, and that gives us 1, 0. And then we multiply that by the length of W, which is 1. So W is 1, 0. Now, we use one of our support vectors to calculate B. Plugging in the values using this point, we get -1 times 1, 0 dot product with 1, 0 plus B equals 1. That gives us a value of B equals -2, and we're done. Notice how the result is the same whether we do it this way or we use a system of equations. Let's analyze some of these things. How did we know what was the direction of W? In this particular example, we just eyeballed it, okay? That's not how you're going to do it in practice. We assumed these were the support vectors, and we drew a line between the negative point and the line that connects the positive points, and that's how we determined the direction of W. How can you do it in practice? If you assume that these are the support vectors, and you remember that the dot product of two vectors is 0 if and only if they're perpendicular or orthogonal, then we know that the direction of W should be perpendicular to the line that connects the two positive points. So we can calculate the direction between the two positive points by just subtracting them, and we get 0, 2. Then we want to find a vector that's perpendicular to 0, 2. We can get the direction of W by choosing any vector v1, v2 that satisfies v1, v2 dot 0, 2 equals 0. Doing so gives us that v1 can be anything and v2 must be 0. So we choose anything to be 1. If you actually want to create a system of equations to solve here, then you can use any scalar multiple of 0, 2, that is, the vector that connects the two positive points, as another vector that should also have a dot product of 0 with the direction of W. We choose 0, 1. Solving these two equations gives 2v2 equals 0 and v2 equals 0. So again, we're in a situation where v2 equals 0 and v1 can be anything. How did we know these were the support vectors? The short answer is we didn't. Again, this is an eyeball sort of problem. So we're doing an intuitive problem. We're not actually solving it step by step. So let me show you how you would actually solve it step by step. There's a finite number of points, which means there's a finite number of possible support vectors. So what you want to do is you just check all of them. So we do a guess and check. Let's start by taking pairs of points. Let's start with these two, because why not? The hyperplane would look something like this. If we assume these two are support vectors, then we draw a hyperplane and then we say, okay, did we get everything right? How can we check if everything is right? Well, if wx plus b times y is greater than or equal to 1. We got this point wrong. If we got a point wrong, that means we can't have these two as our support vectors. So we immediately move on. Now, if we assume these two are support vectors, we get a line like this. Still getting this one wrong, so this one can't be it. Okay, what about these two? Now we're getting this one wrong, so these must not be the support vectors. And these two. Still getting this one wrong, so these are not the support vectors. Now if we choose these 2 points as support vectors, we get a line like this, and we actually get everything right. So we check to see if we got everything right. Now we need to compute the margin. It might seem like the margin is the distance between the negative point that we've decided is our support vector and the hyperplane. But that's not true because we're just picking support vectors at random. When the support vectors are the real support vectors, that is exactly what the distance will be. But for now, we have to calculate the distance from every point to the hyperplane. And we're going to find the distance by calculating w dot x plus b over the length of w. And we're going to find that this point is the closest to the hyperplane, and therefore it defines what our margin is. Then, after we've compared every single double of points, every single pair, we're going to compare triples of points. This will give us a line something like this. What we want to do here is what we did before. We want to connect the 2 points from the same class and then draw a line from the other class to the line that connects the same class. So basically you want to create a triangle and identify the vector that is the height of the triangle. We want to continue the same process when we use 3 support vectors, checking for 100% accuracy and then computing the margin. When will we have 3 support vectors instead of 2? You want to look for a situation where the negative class, or sometimes the positive class, depending on what you're working with, the point that's by itself, when you draw the direction of w, it hits a line that connects the 2 points from the other class. If that doesn't happen, right, like in this situation, when we have this negative point and we connect it to the line that connects these 2 points, it doesn't actually provide any additional value, this point here, because if you just use these two, you'll get the exact same boundary. You have to check all combinations of pairs and triples of points. So the algorithm, roughly, the guess and check SVM algorithm, it runs through all combinations of pairs and triples of points as possible support vectors. So you're just looking at all the data and you're saying, okay, well, I'm going to choose pairs of points, one from positive, one from negative. Maybe these are my support vectors. And then you assume they're your support vectors and calculate W and B, check for 100% accuracy on the training data, calculate the margin, and save the margin, the W and the B. And then you do it again for the next pair and the next pair. And then you do it for all the triples. And then at the end, you return the W and B that give the maximum margin. And that's it. In this video, we covered the hard margin SVM, the soft margin SVM, kernels, the dual form of the SVM, and we went through a hard margin SVM example that you can do by hand using guess and check. The next topic in this class will be bias and fairness in machine learning.